All right, so this one's going to be pretty short. This is the beginning of chapter 3, chemical reactions and quantities. By the end of this chapter, you're going to be able to, if I tell you I'm giving you this much stuff to react, you should be able to tell me how much stuff I'm going to make to produce when I do a reaction. That's kind of the most important part of chemistry is if I put these things together, what can I make and how much can I make and what are its properties, right? So talking about chemical equations. So what is a chemical equation? A chemical equation is something in chemistry that one describes a chemical reaction. So it kind of tells me what's going on with the chemicals, the molecules, the atoms, the bonds, that type of thing. It's going to involve some type of rearrangement of atoms to make different bonds and such. So it's going to rearrange the atoms. So now I get different molecules. That's all a chemical reaction is. So it breaks bonds, makes new ones, I get different molecules. Okay, fundamental principle for chemical equations is the law of conservation of mass or matter or whatever you want to call it. But things can't be created or destroyed, right? If I start with this many atoms, I also have to end with this many atoms. And that's something very important to remember. So atoms cannot be created or destroyed. Okay, they can only be rearranged when we're doing chemical reactions. So this is a chemical equation. I'm going to kind of break it down. We're going to use a lot of chemical equations this year. So there's some terms that you need to know. So first of all, anything on the left side of the arrow is considered a reactant. Anything on the right side is considered a product. Okay. Other things we need to pay attention to. Coefficient is what this is called. This is a coefficient, a number that's in the front. Okay, the little numbers, we've kind of already talked about these a little bit, are called subscripts. Okay. And these little letters in parentheses here tell you the states of matter. So you can be solid or liquid or gaseous, or the other one I'm going to add is aqueous, which means it's dissolved in water. Okay, so those are the states. The subscripts tell us how many atoms are in that molecule, and the coefficient tells us how many of the molecules. So coefficient, let's see, it tells me the number of those molecules in the reaction. In a reaction. I abbreviate reaction RXN, just so you know. So this means I have two H2 molecules. Okay, so two things that are H2s. That's what that means. The subscript tells you the number of atoms in that molecule. Okay, so each hydrogen molecule is two hydrogens bonded together. Each oxygen molecule is two oxygens bonded together. And then over here, I have two waters. A water molecule is two hydrogens and an oxygen all bonded together. Okay, so when we are balancing equations, it is important to note, that's why I put this in all caps, that the subscripts cannot be changed. Okay, O2 is oxygen, always. If I change it to O3, I made a completely different molecule. O3 is ozone, it has completely different properties. Okay, water is H2O. If I try to change the little subscripts, I actually change the molecule. If I do H2O2, when I'm trying to balance it, I can't do that because I made a totally different molecule. H2O2 is hydrogen peroxide. Okay, so you have to, when you are balancing, don't change the subscripts. The subscripts are based on the names. They're based on balancing those charges that we talked about in the last unit. So don't change the subscripts when you're balancing. You're going to balance by adding or changing coefficients. Okay, so there's a method to the madness. Unfortunately, most people like to say it's kind of a guess and check. Essentially what you're doing is you're figuring out by inspection and then checking it and checking it. Okay, so double check that all of your atoms add up to one side and the other side. Okay, the other thing is you're going to, I would anyway, use a tally to kind of keep track of how many of each element you have. Use tally for each side. Maybe because you should have the same number of atoms on one side as you do on the other side. And you want to start with elements that occur once on each side. So like the reactant side and the product side. That'll kind of make it easier. So I have a couple of more tips. If you've got polyatomic ions, do those first. Do polyatomics first, as long as they stay together anyway. If it's a combustion reaction, so something that makes carbon dioxide and oxygen, do C and then H and then oxygen. It'll kind of help. Also with combustion reactions, if it's not balancing and you keep getting this even odd thing, try to double the complicated molecule or the hydrocarbon. Complicated molecule if needed. And my last one is to do pure elements last. So balance pure elements last. Okay. So essentially, you want everything on the left side equal everything on the right side. So if I'm looking at this reaction, I'm going to make a line, and my two elements are aluminum and chlorine. I got aluminum and chlorine. So what I say when I mean tallies is right now I have one aluminum and I have two chlorines. Over here I have one aluminum and I have three chlorines. Well, my chlorines are not balanced. And I know the least common multiple between 2 and 3 is going to be 6. So I'm actually going to need 3 Cl2s, because that means that I actually have 6 chlorines, 3, 4, 5, 6. And then I'm going to need 2 of these, but that now makes it so I have 2 aluminums and 4, 5, 6 chlorines. So my chlorines are good, but now I got 2 aluminums. So I'm going to have to put a 2 here so they balance out. So that's what I mean by the tally marks. You might be able to do it just by looking at it. Okay. Balancing this reaction, I've got H3PO3, H3PO4, and PH3. Now, remember, one of the tips was if you have an element that's only in one molecule on each side, do that one first. So I'm actually going to do oxygen first. 3 and 4. The only way to get 3 and 4 to balance is to get them both up to 12. So I already know I'm going to have to put at least a 3 and a 4 there. Now my oxygens are fine because 3 times 4 is 12. 4 times 3 is 12. My oxygens are good. Okay, from there, I should look at my hydrogens and my phosphoruses. So I have 12 hydrogens here. I have 3 times 3 is 9 hydrogens here. And I got 3 more over here, and that's 12. And then I have 4 phosphoruses, and I have 3 phosphoruses here and 1 here. Okay, so the way these coefficients work is it gets distributed to the whole molecule because it's like I have 4 of these molecules, just like a coefficient in math. All right, so try to balance these equations and then check your answers. All right, these are what I got. Notice I didn't write a 1 if I only need 1 of something. The 1 is understood. And like that doubling thing I talked about. So down here in this combustion reaction, I had to end up doubling the big molecule and then rebalancing to figure out how to balance best. All right, this is going to be just kind of a quick rundown of the types of chemical reactions. We can get more into different types later. There's technically 5 types of chemical reactions. Okay, and for right now, you should be able to identify these reactions just based on like looking at a balanced chemical equation. So combination and decomposition are actually opposites of each other. What happened to my pen? So these are opposites. Something combining versus something decomposing makes sense, right? So combination is essentially 2 substances combine to make 1. All right. So the generic equation is like A plus B makes AB. All right. An example would be I have 2 aluminum solid plus 3, and these are all balanced equations, liquid, makes 2 Al Br3 solids. So this is pure aluminum combining with pure bromine to make aluminum bromide. Here, that would be a combination reaction. Now decomposition, like I said, is just the opposite. So this would be one substance decomposing, or breaking, decomposes to make, it could be 2, it could be 3, several new smaller substances. So generically, I would have AB breaking down into A plus B. That's what the reaction would look like. So this is what happens with sodium azide. Sodium azide is actually used in airbags, 2Na, to fill them up really quick. So this is an example reaction into gas. So I start with one compound and it breaks into two different compounds. Notice I'm not paying attention to the coefficients. They don't actually affect what type of reaction it is. You want to look at the compounds and the elements that are made or used. Okay. Next, we have replacement reactions. So a single replacement is when one element switches places with another element. So one element replaces another. Okay, so generic equation would be I have an element and I have a compound, and like my A and B are going to switch places. So now A is going to be with C and B is going to be by itself. Okay, so here I've got mercury nitrate, aqueous. This happens a lot with aqueous solutions. Sodium iodide makes HgI2 solid and 2NaNO3 aqueous. Okay, so I have sorry, this is the double replacement reaction. Hang on, let me move this down. Sorry about that. A more appropriate example would be like copper solid. So one single element reacting with silver nitrate, AgNO3 aqueous. So single element compound, and then the silver and the copper actually switch places. So now I end up with copper to nitrate and solid silver. Okay, something along those lines. Double replacement then is when two things switch places. So essentially you have compounds that switch partners. Compounds switch partners. So like they switch cations essentially to make new things. So you would have one compound AB and one compound CD. So like these guys would switch, my cations would switch. So now I would have C with B and A with D. Okay, so the cations just switch places essentially. So here was that example I had before, mercury nitrate and sodium iodide. So that's two compounds. So they just switch their anions. So now I have mercury with iodide, which is a solid, and sodium nitrate, which is aqueous. Okay. And finally, combustion. You're probably most familiar with combustion equations, right? In order to have combustion, they have to react with oxygen. It's usually a hydrocarbon reacting with oxygen, and it produces a flame. And we're generally going to get water and carbon dioxide out of it. So it's usually a hydrocarbon, like I said. So C something, H something reacts with oxygen and makes CO2 and H2O. Okay, real life example would be methane, right? CH4 is methane. If I light it, that's what's in the Bunsen burners in the lab. Methane reacts with oxygen. Remember, you have to have oxygen, and it makes, I'm balancing that, that's a 2. It would produce a carbon dioxide and 2 waters. Okay, so you should be able to look at an equation and be like, oh, that's a combustion reaction, or oh, that's a single replacement reaction, so on and so forth. All right, last thing I want to talk about today is formula and molecular weights. So formula weights, molecular weights, molar mass or molar weight or whatever you want to call it, these are all essentially the same thing. It's just the mass of a molecule. So when you see me write FW, that stands for formula, MW stands for molecular weight. The only difference is one is for ionic and one is for covalent, because formulas are ionic, molecules are covalent generally. So how do I find these? It's the sum of the atomic weights, right? Those numbers from the periodic table that have decimal points. This is for an ionic compound. And molecular weight is the sum of atomic weights in a covalent or molecular, same thing, compound. Okay, so if you're thinking about like water, we did that one earlier. We found the molecular weight of water. It's the weight of the molecule. All right, so last thing I want you to do is find the molar mass for these molecules. Now, hey, you have to remember your naming as per usual. Iron 3 sulfate. So first I got to figure out what the formula is. So iron is Fe. It has a 3 after it, so that means its charge was +3. I have sulfate here. Now, if it ends in an ATE, that means it's going to be on your period or on your polyatomic ion chart. Sulfate is SO4 2 minus. So if I do my little switcheroo here, crisscross, I get Fe2, and then I need 3 sulfates. So SO4 3. Now I got to break it down and add them up. So I need to find iron's molar mass, sulfur's molar mass, and oxygen's molar mass, and multiply them by however many I have. So iron, for example, is 55.845, and I have 2 of them because it has a subscript of 2. And so I got to do that, and that one's 111.69. I have sulfur is 32.06 from the periodic table. I have 3 of them, so that would be 96.18. And oxygen is 15.999. And I actually have 12 of them. Remember these, if there's parentheses, this is going to distribute. So I have 3 sulfurs and I have 12 oxygens. Okay, so that's 191.988. And you add them all together, and my final formula mass or formula weight is 399.859 atomic mass units, right? We've been using atomic mass units. Now there's another unit we're going to start talking about. It's called grams per mole. You might have noticed that I said molar mass up here. We're going to talk about what a mole is in the next part of the unit. But these are going to be the units you're going to find. So all you have to do is add up the numbers essentially from the periodic table. So you try glucose really quick, check your answer here, and then we'll be done. All right, molecular weight I got for glucose was 180.156 atomic mass units. If you have questions, let me know. Email me or email Adara and let us know.